we're going to start the conversation about something called mutually exclusive events and independent events. It's broken up into two chunks. So today we'll do mutually exclusive, tomorrow we'll do independent. At that point, you'll be able to do everything in this whole heap. Okay? So, again, just like the other day, there's a lot of reading with this stuff. So, mutually exclusive events. If we remember back in our old questions when we did set diagrams, like Venn diagrams and stuff, we had a symbol that looked like this. And what did that thing mean? It means A and B. So it's all things that are in A and in B together, right? It's the intersection of the two. So we also learned that this is the opposite. And this would be A or B. We just need to remind ourselves what those things actually mean so that later when we're talking about them again, it's like, what does that symbol mean? So this is A and B. It has to be in both groups. This is A or B, so it includes everything that's in either group. Do you remember that? Good. All right. Let's start off with an example. So an example, a standard die is rolled. Remember, a standard die has 6 sides. So a 6-sided dice is rolled. Let A represent an even number being rolled. So group A is an even number being rolled. Let group B represent an odd number being rolled. So we took a dice, we rolled it. Event A is we got an even number, event B is we got an odd number. Fill out the diagram below for what possible results could be in group A or group B. So for group A, what could you roll that would be an even number? 2, 4, 6. Correct? Those are the even numbers. If you rolled event B, that means you rolled an odd number. So that means you rolled a 1. Rolling a die, you could roll a 1. No? We don't count 1 as prime. Oh, cards. There's no 1 in the deck of cards. Yeah. No, that's okay. On a die, the 1 is still 1. So that's all the ways you could make event A happen. That's all the ways you could event B happen. Simple, right? All right. For each of the question before, list the outcomes for each event. So what are the possible outcomes for A? 2, 4, 6. What are the possible outcomes for B? 1, 3, 5. Question 3 says A and B. So what number is in A and in B? There's none. So we call that set the null set. So it's a 0 with a line through it. There's nothing in A and B. There's no way that could happen. The fourth question is A or B. So all the things that could happen in A or B would be 1, 2, 3, 4, 5, 6. That's a lot of review, hopefully. And then once the Venn diagram is made, that should look like review. Agreed? Gorgeous. Calculate the probability of the following. So now we're getting back to what we did yesterday. What's the probability of A happening? So event A. Yeah, you got it, Brahma. What is it?
3 over 6.
It's 3 over 6. Why is it 3 over 6? Because you want the number of outcomes you want to happen on the top. So there's 3 possible events that could happen that you wanted. Right? You could have rolled a 2, a 4, or a 6. So there's 3 possible outcomes you wanted. And you divide it by the total number of outcomes. So when you're doing probability, it's what you want divided by what you could have got. So if we do this for B, same thing. probability of B happening would be 3 divided by 6. There's 3 possible things in event B that we would like to have happen, but there's 6 possible events total that could have happened. 3 divided by 6. Triple I. This is, what's the probability of A and B happening? How many things are in A and B? There's 0. So you would have 0 possible outcomes divided by 6 total outcomes that could have happened. That means it's not even possible, correct? And it makes sense. There's no way I could roll an even number, and there's no way I could roll an odd number on the same roll. That's just not possible. What's the probability that I get A or B? So how many things could I get A or B? Yeah, it'd be 6 out of 6. Because A or B means everything. There was 1, 2, 3, 4, 5, 6. If I get into any of those, I'm in A or B, and I'm happy. Divided by the total number of things, which is 6. So that's 100% certainty it's going to happen.
So like for the probability of A and probability of B, does that have to be 3 over 6?
You could render that as a question of 1/2. That'd be the same thing.
Okay.
Yeah. Those are just simplified fractions. All right, why we're doing all that? The question that we just did is an example of a mutually exclusive event. So we read off all of the slides. In the previous example, we noticed that A and B, so A and B, had no elements in it. The reason it had no elements in it is because we were doing a mutually exclusive event. So A and B are mutually exclusive events, meaning that there's no way they could both happen at the same time. That's what mutually exclusive means. Mutually exclusive means there's no way that event A and event B could occur at the same time. A really common or simple one. If event A was it's raining outside, and event B was it's not raining outside. Those are mutually exclusive events. There's no way they can both happen at the same time. It's either raining or it's not raining. So they go through and they talk about it a little bit. This means we can define mutually exclusive events as events that cannot have any common outcomes. There's no way they share something that happens. You may also notice that in that example, those things weren't just mutually exclusive, they were complementary. So complementary means complete opposites of each other. Remember we talked about that on the very first day. Sets that are opposite of each other are complementary events. Same thing with my raining example. Event A is it's raining outside, event B is it's not raining outside. Those are complementary events. They're complete opposites of each other. Another thing we notice, if you look back at this slide right here, this situation was not a coincidence. If you have mutually exclusive events, that means there's no way both things happen at the same time. That means the probability of them happening at the same time is always going to equal 0. So that's what this is saying right here. If you have mutually exclusive events, you know A intersect B equals 0. So you know that the probability of A intersect B equals 0. And that's a way you can tell if things are mutually exclusive or not. You could test that formula. If two things do share an outcome, we don't have a fancy name for that. We just say they're not mutually exclusive. Okay, mutually exclusive examples. So we're going to go through each one of these and we're going to say, is it mutually exclusive? Is it not mutually exclusive? Example 1. Event A is a number less than 4 is rolled on a die. Event B is a number greater than 3 is rolled on a die. My suggestion is to write out the things that could happen for each event. So, for A, what could we possibly roll that would be this event? We could roll a 3, that would be less than 4. A 2, that'd be less than 4. Or a 1, that'd be less than 4. Event B, a number greater than 3 is rolled. Write out the things that could fit that. 4, 5, 6. And now it's easy to check if they're mutually exclusive or not. Do they share anything? Do event A and event B have anything in common? Definitely not. So this is mutually exclusive. Does anybody have any questions about what defines mutually exclusive? I want you to try the next 2 on your own. If you need to draw out all the things that could happen, that's cool. Or you can just do it in your head, that's also cool. So if we read experiment number 2, it said a card is drawn to the standard deck. The first event would be a face card is selected. So that means I could have drawn out Jack of Hearts, Jack of Diamonds, Jack of Spades. Boom. Let me say that's the clubs. Because I think that spade is. Or the Jack of Spades. That's still off of spades. You could also do that for queens or kings or aces if they counted that as a face card, which they don't. The second event was a club is selected. That's a lot of things. That could be the 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace of clubs. Is there anything that's going to be in both groups? Yeah, like if you look at our example right now, the Jack of clubs right here would be in both groups. That's a face card and it's a club. So that would be in both events. So right there, you know that these things are not mutually exclusive because there's something that could be in both groups. The next experiment, 2 dice are rolled. Event A is both dice show the same number. So I've written out all the possibilities of you getting 2 dice that show the same number. You could get 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. That's the only things that you could do that have the same number on both die. Event B says the dice values add to be 9. So I wrote out all the possible rolls I could make that add to be 9. I could have 6 and a 3, that would add to be 9. I could have 5 and a 4, that would add to be 9. Is there any other dice roll I could make that would add to be 9? None that I can think of. Do either of these in set B fit into set A? There's none in common. So if there's none in common, it's not mutually exclusive. Did that answer your question? Please start.
Dice experiment 1 was mutually exclusive and there's nothing that went into each other.
Oh, sorry. Yeah, it is mutually exclusive. I wrote the wrong thing. They don't have something in common. Sorry, that's no wonder you guys are confused. I wrote out the wrong thing. Yeah, they are mutually exclusive because there's not one in both. Great. Mutually exclusive events, when we're talking about them right now, probably seem pretty simple. Independent events is going to be what we do tomorrow, and they're pretty similar. So people get them confused. So that's why we're just really hammering home, mutually exclusive events are things that can't occur at the same time. All right. There's 2 formulas for mutually exclusive events. They're both right there. We're going to talk about them. These are formulas that are given to you. Okay, so these formulas will both be given to you. They're both for when things are mutually exclusive. If events A and B are mutually exclusive, then this formula is true. And this formula says that the probability of A or B happening would equal the probability of A happening plus the probability of B happening. If we go back in time and we look at our example, and our example was dice being rolled even or off, the probability of A happening was 3 over 6. The probability of B happening was also 3 over 6. If you added those together, you would get 6 out of 6. Correct? The probability of A or B happening was 6 out of 6. So it does work. It works for mutually exclusive events only. So this formula is only if you're mutually exclusive. You can't use it any other time. If you're not mutually exclusive, then what you need to do is use this formula, which says the probability of A or B happening is the probability of A plus the probability of B, but then you subtract out the fact that you've double counted a few things. And that would be the probability of A and B happening. So that formula is for when you have things that are not mutually exclusive. Does those make sense where they're coming from and why they're happening? Basically, remember when we were counting things before and you always have to subtract out double counting? That's what this is. It's subtracting out the fact that you had to count something twice. Alright, examples of mutually exclusive events. We got a bunch of them. There's a bunch of them on your unit assignment as well. So you'll notice that after we talk about mutually exclusive events, we basically just go into a bunch of probability examples. And after we talk about independent events, we're going to do the same thing, because they're just mixed all together. So this first example says, which pair of events on the Venn diagram are mutually exclusive? I'll give you one pair that's mutually exclusive. A and B could never happen at the same time. They never cross each other. There's no way I have something in A that's also in B. So one set would be A and B. Those would be mutually exclusive from each other. It's saying which pairs of events, right? So that's what I'm trying to that. If you said this, A and B, you just talk, oh, okay. I'm just going to say A and B. You're saying the intersection between them. That's all that's saying. They're not telling you anything. If you said A and B equals 0, that would be proof that it's mutually exclusive. Alright, I want you to write down the other pairs. There's 1, 2, 3 more pairs that you can write out. So you were looking for events that couldn't happen at the same time. So there's no way that A and C could happen at the same time because they don't cross each other. A and D couldn't happen because they don't cross each other. The only other one that's a little bit tricky is the fact that B doesn't ever intersect with D. They both intersect C, but they don't intersect each other in the same spot. So B and D would also be mutually exclusive events. Alright, example 2. Use the given information to determine if events A and B are mutually exclusive. So we're going to test to see if these are mutually exclusive. We don't know what event A is. We don't know what event B is. So it's not like we could read it and then figure it out. All they're telling us is the probability of event A equals 1 over 4. The probability of event B happening is 1 over 3. The probability of either of those things happening, A or B happening, would be 7 over 12. We don't even know what these events are. How can we tell if they're mutually exclusive, Jaden? If you add them together, they should equal A or B. So if we look back at our formula, it says if things are mutually exclusive, then the probability of one plus the probability of the other should equal the probability of either or. So you can test this out by adding together these probabilities. You can go 1 over 4 plus 1 over 3. Throw that thing in your calculator. It's going to give you an awful decimal. And then you're going to go math fraction. And it's going to give you a much nicer decimal, or fraction. If you do it, you should get 5 over 12. You want to test that theory, though? Is it 7? Wait a minute. Yeah, I did times 2, not times 4. So you add these in your calculator. Go 1 over 4, enter, plus, and then in brackets 1 over 3, enter. That'll give you a decimal. The decimal should be 0.588888. Is that right? 58333. Yeah, that makes sense. 5833333. You go math, fraction, and that'll tell you that it is equal to 7 over 12. This confirms the fact that P of A plus P of B equals P of A or B. If it hadn't equaled, then they would have been not mutually exclusive events. But because it did equal, it these formulas that we're going to get, that's what also can make mutually exclusive and independent kind of different. Because independent is also going to have some formulas that we get tomorrow. All right. Review examples from probability, because that's what you need to get at. Example 3. A card is drawn from a standard deck. Use formulas to determine the probability that a 9 of diamonds or a heart is drawn. You could use anything you want. So if you want to use a tree diagram, if you want to use your noggin, if you want to use a chart, that works too. The formula that it's referring to is what's the probability formula here? Number of desired outcomes, so what you want to have happen, divided by the total number of outcomes. Number of desired divided by the total number of outcomes. So in this situation, we want a 9 of diamonds or a heart to be drawn. So how many possible things get drawn that we would be happy with? 14. There'd be 14 because there's 1 for the 9 of diamonds. And if you remember from that chart we wrote out, there's 13 hearts in it. And these are mutually exclusive things. Nice catch. There's no way that this 9 of diamonds is included in the hearts. Those are mutually exclusive things happening. So you can add them together and know that there's 14 desired outcomes. You then divide it by, what's the total number of outcomes? 50. You could have drawn any of those 52 cards. That's your probability. You should write it into simplest form, which is 7 divided by 26. So you math fract that thing to get 7 out of 26. I want you to try B on your own. So it says a 9 or a heart is drawn. Very similar question, but it is different. So give it a shot. And there's a trick to this one. The way I would think this thing through. I want a 9. How many 9s are in a deck? There's 4. There's the 9 of diamonds, 9 of hearts, 9 of clubs, 9 of spades. Or I want a heart to be drawn. There's 13 hearts. Hopefully you got that part now. The problem is, what are the hearts? There's 2, 3, 4, 5, 6, 7, 8, 9. We've already counted that 9 in this set of 4. So you need to go 4 plus 13 minus 1. Because you don't want to double count. Yeah, if you just said there's 12 other hearts, that would also work. Or if you said there's 3 9s that aren't hearts, plus the 13 hearts, that would also work. Remember to check to see if you're double counting anywhere. That's where probability can get a little tricky. In this case, these were not mutually exclusive events, right? There was something that landed into both of them. The 9 of hearts was in both. So you had to subtract that when you're doing your probability. That means that we have 16 desired outcomes divided by the 52 possible outcomes. Did I have that right? Because there's 4 9s plus 13 hearts, and then you subtract the 9 of hearts because you counted it twice.
Oh.
You counted it as a 9 and you counted it as a heart. That's fair. And then what do we do here? We simplify that thing. You'll math, we go frac, and what do you get instead? 4 over. Beautiful. That's the probability you get a 9 or a heart. If you ever get good at poker, you have to have a lot of money. Yeah. Yeah. All right, example 4. Blocks of different shapes and colors are placed into a bag. There are 3 cubes, 2 pyramids, and 5 cylinders. 3 of those cubes, one is blue, one is red, and one is green. You do the same thing for the pyramids. One is red, one is yellow. For the 5 cylinders, one is blue, one is yellow, and 3 of them are red. You draw something out of the bag. So all those shapes are in the bag. You draw one out. What's the probability that you picked out a pyramid or a cube? So if you want to figure out the probability that you got a pyramid or a cube, you need to figure out the total number of things that you would want to have happen. So how many pyramids could I draw out? There's 2 pyramids. There's the red one and there's the yellow one. How many cubes are there? There's 3 cubes in there. Is there going to be any intersection between those? Are any of my pyramids going to be cubes? No, otherwise there wouldn't be pyramids. Are any of my cubes going to be pyramids? No, or else there wouldn't be cubes, right? So these things aren't double counting anymore. So what's the total number of desired outcomes? There's 5 desired outcomes. You divide it by the total number of possible outcomes. So how many possible outcomes were there? Well, there was 3 cubes plus 2 pyramids plus 5 cylinders for 10 total shapes. Five divided by 10 has to be 1 over 2, or 0.5. Okay. I want you to try B and C on your own. They're tricky. You're doing the same thing. Alright, so if we're doing those 2, if you're doing B first, so a red shape isn't picked. So you want to find the number of outcomes that wouldn't be red. There's 1 blue, plus 1 green, plus 1 yellow, plus another blue, plus another yellow. So there's 5 things that aren't red in the bag. There's 10 total things in the bag. So I go 5 divided by 10, simplify that to be 1 over 2. As a decimal, you can still put 0.5. C is the trickier one. So it says a red shape or cylinder is picked. So what I did is I counted the number of red shapes, and I got 5 red shapes total. And I counted the number of cylinders, and I found that there's 5 cylinders total. Unfortunately, 3 of those cylinders are red. And I've counted those things twice. They're part of this group of 5 because they're red, and they're part of this group because they're cylinders. So I need to go, the groups I have, 5 plus 5, minus the 3 that are in both groups that don't want to double count. That gives you 7 total things that you can pull out that you like. So your odds are, sorry, to not mix those words up. The probability is 7 divided by 10. I had said odds. You should mix up the words odds and probability, right? They mean specific things. Odds would be 7 colon 3. 7 things you do want, 3 things you don't want. Right? That's odds. So I shouldn't mix those words up. Why is it out of 10? Because there's still 10 shapes in the bag. So if you imagine you actually had this bag full of 10 things, there was 10 of them. Okay. As a decimal, it would have been 0.7 if we're doing decimals. All right, so more probability. Oh, that's the end of probability examples. Beauty.